right, today we're going to talk about quantum numbers. Now, through these four quantum numbers, what you're going to be able to do is provide the exact location for any electron within an orbital diagram. You could imagine these quantum numbers as an address for these electrons, just like your home address. An address can start very generic. For example, you might give someone the city you live in. Then it starts to get a little bit more specific. You might tell them what street you live on. Further than that, you might give them your house number. And sometimes, maybe if you consider a duplex or an apartment complex, you would give them your apartment number. All four of these make up your address, just like these four are going to make up the electron's quantum address. Now, before I get further into each of these individual quantum numbers, there are a few principles that I want to cover. The first of which would be Heisenberg's uncertainty principle. And this simply states that we cannot know precisely where an electron is at any given moment in time. We can only express the location of an electron in terms of probable location. So again, we're talking about probability. When we talked about orbitals, we learned that they're probability maps where the electron probably would be. Similar here, we're talking about probable locations, or the probable address of your electron. The second principle I'm going to cover is the Pauli exclusion principle. And this states that in an atom, no two electrons can have the same set of quantum numbers or have the same location. Imagine a 2p orbital. Drawing an orbital diagram here. If you have an electron in, say, this first box, that is the only electron that would be in this box, in this orbital, in this orientation, pointing up. If you were to put a second electron in, it would point down. It wouldn't be exactly the same. No two electrons can have the exact same location. Okay, that's the Pauli exclusion principle. All right, so let's go ahead and move on now to talk about our first type of quantum number. Our first type of quantum number is, again, the most generic. It's our city, if we're using the analogy. And it gets abbreviated with an N. So if you see something asking you for the N, it's talking about the principal quantum number, the most generic. Now, this is specifying the main energy level of your orbital. You can see here for each of these quantum numbers, I've drawn an orbital diagram, and in red, I'm highlighting the part of the diagram that this number is representing. So a principal quantum number is referring to the energy level of each of these orbitals. Energy level 1, energy level 2, energy level 3, 4, and so on. If you were asked what the principal quantum number or energy level N was for an electron, say I draw an electron here, you would report that the N would equal 3. It's the third energy level. Okay, this first one is fairly simple. However, you should notice that each energy level has a different size to it. This third energy level is moderately large, whereas the fourth energy level is quite a bit larger. You could think about this in terms of cities. Some cities are very large. For example, Seattle is a large city, whereas Edmonds is a much kind of smaller or a moderate-sized city. There are very small cities out there, but it kind of just depends on the size, how many electrons can fit in each energy level. All right, so that's the principal quantum number. Let's move on to the next type of number. Our second address number, you could think about it, is going to be referring to essentially the street. The street of the electron. Now, we call this the angular momentum number, which is a lowercase l, has representing it. We use a cursive L because it's easier to tell apart from a 1, so cursive L. Now, the angular momentum number, or the L number, is referring to what type of orbital. So, for example, whether it's an s orbital, a p orbital, a d orbital, or an f orbital. Essentially saying the shape, because an s orbital is a spherical shape. A p orbital is like a dumbbell shape. D orbital is a clover, and f orbital is like a flower. The more difficult part about the L value, however, is that it's not directly what we see in the orbital diagram. We wouldn't ever say L equals S or L equals D. What's happened is we've assigned numbers to represent each type of orbital, starting with 0. So for example, an s orbital is represented with the number 0. A p orbital is represented by the number 1. A d orbital is represented by the number 2. F orbital is represented by 3. G orbital is 4. The orbitals actually continue. The next orbital in line after G would be H, and then I, J. Again, the numbers would go up 5, 6, 7. Okay. Now, again, you'll notice that each of these orbitals, or L numbers, are sized differently. An s orbital is the smallest one. P comes next, D, and then F. And again, similarly, streets have different lengths. Some streets are longer, some streets are shorter. Sometimes you'll be asked to calculate how many possible L values you can have for a certain n. And that's where this equation that I've highlighted in pink comes into play. If you know your n value, say, for example, we wanted to know how many L's or how many orbitals were going to be in an n value of 3, the third energy level. What you would do is solve. It's going to be a range. The range is always 0 to n minus 1. And if you know n is 3, 3 minus 1, that means we're going to get a range of 0 to 2. And so if I look at my L values of 0 to 2, that would correlate with the orbitals S, P, and D. And when we look at the orbital diagram itself, you can see that this is true. S, P, and D. What this allows you to do is for larger energy levels, for example 6, you would be able to calculate how many orbital types would be there, even if you can't picture the orbital diagram yourself. So this is an important equation, and we'll reference it as we continue. All right, moving on. Our next magnetic quantum number is our next number, and it's abbreviated with an M sub L right here. This is again getting more specific. This is representing the house number as our address analogy. This magnetic quantum number is going to specify which specific orbital, kind of suborbital we're talking about. You can see I've highlighted the boxes this time. As we learned before, these boxes represent the suborbitals. We learned that P has a suborbital of px, where the dumbbell is horizontal. We have a PY, where the dumbbell is vertical. And we have a PZ, where the dumbbell is kind of coming out at you and then away from you. It's hard to draw, but you get the point. Come on. Ugh. Oh well. Now what we do is, now what we're going to do once we've identified the different types of suborbitals within the p orbital, again we assign numbers to represent these certain orbitals, suborbitals. And the way we assign the numbers is the middle box gets a 0. And then we range in the negative direction and the positive direction from there. So the next one over would have a -1 value, and the next one over on this positive direction would have a +1 value. So we've got -1, 0, +1. If we do the similar process for a d orbital, the middle box would be 0, then we would have -1 and -2. In the other direction, we would have +1 and +2. What this allows us to do is to locate which box is being used for a certain electron. For example, this electron that I just drew would be in the N value 2, would be in L value 1, and would be in M sub L value of 1. Okay. Now, you don't have to put the 0 in the middle and then range from there to know what numbers to use. These numbers, these M sub L numbers, are related to the L value. Think back, what was the L number for P? Let's go look. A p orbital has an L value of 1. So notice we ranged from -1 to +1. Let's do the same for D. What was the L value for D? I also have it here, I suppose. The L value for D is 2, so we range from -2 to +2. What is the L value for F? If you go back and look, F, L value is 3, so we would range from -3 to +3. Okay? So this highlighted in pink, again, is an important sort of equation for figuring out the M sub L possibilities if you know the L value. All right, let's move on to our last quantum number. Our last quantum number is the spin quantum number. And this is where we get the most specific. For example, if in our address analogy, it would be our apartment number. Okay. We summarize this as M sub L, S for spin. This quantum number is going to communicate whether the electron has an upspin or a downspin. Now, really quick, the electrons aren't actually spinning up. They're either spinning clockwise or counterclockwise. And anytime there's a clockwise spin, that creates a up spin. I don't know how to explain it. And counterclockwise means down. But for the most part, we just refer to it as upspin and downspin. Now, anything with an up spin gets assigned the number +1/2. And anything with a downspin gets assigned the number -1/2. So any electron would be able to be identified even further. Let's identify this electron right here. The N number would be 4. Okay. The L number would be 1. The M sub L number, right here, this first box, would be -1. And the ms number, because it's an up arrow, would be +1/2. Okay? So as you start encountering problems that you have to solve, your first example here, what you'll find is they will often give you the value of n and ask you to determine possibilities from there. Here, you're asked to calculate L. And so what you should do is recall the equation for L. L equals a range of 0 to n minus 1. So if you plug in n of 5, you would have a range of 0 to 4. Now, it is also asking for you to designate which orbital matches each L that you're giving. So, what you would see is the first L of 0 would be orbital s. L of 1 is p. 2 is d. 3 f. 4 and g. Now, beyond that, it does also ask for you to determine the m sub L, which uses a different equation. To find the m sub L, you are going to have a range of -L to 0 to +L. So as we look at L of 0, we would really only have a range of just 0 for m sub L, because there's only one way to orient an s orbital. If we look at L of 1, we would range from -1 to +1, because there are 3 ways to orient an p orbital, as we learned, x, y, and z. Now beyond that, L of 2 would be a range of -2 to +2, 5 ways to orient a d orbital. L of 3 would be -3 to +3 for the m sub L, because there are 6 ways to orient an f orbital. Okay, so that's our first example. Let's go to our first practice problem. For this problem, what I would like you to do is, using n equal to 6, determine the possibilities for L. And please label whether they are S, P, D, F, G, H. Okay? Go ahead and pause the video now, solve this, and then press play, and I'm going to solve it here. So if n equals 6, and we're trying to solve for L, again, you're going to use the equation of a range 0 to n minus 1. So if you know that your n is 6, that means we're going to range from 0 to 5. So we're going to get L values of 0 to 5. Also, we need to label whether they are S, P, D, what types of orbitals essentially. L0 is always S, 1 is P, D, F, G, and H. And that's all this question asked for. So let's go ahead and move on. Here's your next type of problem that you're going to encounter. This problem is asking you which of these sets of quantum numbers are incorrect and what is wrong about it. So firstly, what you're going to want to do is consider the set and what possibilities would be correct. So for A, what you would do is take n equals 3 and then solve for the L values possible from an n value of 3. Using this equation, we would find that L values would range from 0 to 2. Now, after selecting L of 2, you would then solve for the possible M sub L numbers. If L is 2, that means we're going to range from -2 to +2. As we check each of these quantum numbers, we see that n of 3 is a valid number. L of 2 is a valid number. and m sub L of 2 is also a valid number. So this A is a valid set of quantum numbers. Go ahead and pause the video here and solve for B, C, and D, and then press play to hear my answers. The answer for B, you would have to solve for n equal to 4, which would give you a range of 0 to 3. And if you look at an L of 3, you would get a range for m sub L of -3 to +3. With these possibilities, n equal to 4 is valid. L equal to 3 is also valid. But there's no such m sub L 4. So this is an invalid address because of the m sub L. Now let's solve C. First of all, n equals 0. Think of an orbital diagram. On an orbital diagram, do you ever have an energy level of 0? No. It always starts at 1s. 1s is the smallest energy level. There's no such thing as n equals 0. So right off the bat, C is invalid. Moving on to D. If D has an n value of 2, that would give us possible L's of 0 to 1. But right away, you should notice that the n, yes, is possible, but L, there's no such thing as a negative L. So that would not be valid because of the L. Okay? The next type of problem that you'll have to solve is where you are asked how many electrons can have this particular address. One trick to these is sometimes they will give you an invalid set of quantum numbers, in which case the amount of electrons at that address or set of quantum numbers would be 0. So when we look at A, as before, you notice that n of 0, that's invalid. So there would be 0 electrons at this set of quantum numbers for A. For B, you would again consider each of these quantum numbers to determine whether it is a valid address. And if it is, determine how many electrons could fit at that address. Pause the video now and determine whether or not B is valid, and then press play and I will show the answer. If n is 2, that would give you L's of 0 to 1. And if L is 1, that would give us m sub L values a -1 to 1. Within m sub L of -1, the possible ms values would be +1/2 and -1/2. This is a valid address, and it's a complete address. And due to the Pauli exclusion principle, we know that only one electron can exist at a certain full set of quantum numbers. For C, they've only given you a partial address, only the n value. So it's asking how many electrons can fit in the third energy level. To solve this, what you would do is set up n equal to 3 and determine the L's from there. 0 to 2. From here, what I would recommend is thinking of the L's in terms of their actual orbital, for example, an s orbital, and then consider how many electrons are in an s orbital. And then add up all the electrons from there. Go ahead and pause and solve on your own for how many electrons would fit in n of 3. As you complete this answer, you would have also a p orbital and a d orbital. The s orbital has 2 electrons, the p orbital has 6, and the d orbital has 10. Add those up and you get 18. There would be 18 electrons in C. So go ahead and pause, solve D and E on your own, and then press play for my answer. For D, n of 2, you would get L's of 0 to 1, which means your L is invalid. 0 electrons here. N of 1, your L's would be 0, and your ML would be 0. Not possible to have an M sub L of -1 in this scenario, so invalid, 0 electrons. For practice, what I'd like for you to do is copy this chart into your journal and solve for all the possibilities. I'm going to show the answer for n of 2. You can pause now and then check your answer, or watch. As n is 2, that would mean we have L's of 0 to 1. When L is 0, we would have M sub L of just 0. But when L is 1, we would have M sub L of -1, 0, and +1. For both of these, the possibilities for MS is always +1/2 and -1/2. That's what I would want you to show for an entire line. Okay? Go ahead and finish this on your own. Next is simply more practice. Pause the video and solve for which of these sets are invalid, and cross out what number was causing the number to be invalid if that was the case. The answer for A is valid. The answer for B is invalid due to L. The answer for C is valid. And the answer for D is invalid due to M sub L. Once again, pause the video, solve these problems on your own, and then press play to hear my answers. The answer for A is valid. The answer for B is invalid due to M sub L. The answer for C is invalid due to N. And the answer to D is invalid due to L. Well, I hope this video helps. Good luck!